Devin Tracy, and he's going to tell us about, wait, so who really won the election?
Well, thanks for reading my first slide before we got
Oh yeah, sorry.
So we can just skip that one, I guess, right? So I'm going to talk to you guys about voting theory mainly, is what we're going to talk about today. We're going to prove Arrow's theorem by the end of the talk. And before we do that, the chart in front of us is something that is probably almost alien to Americans. Because when we vote, we only cast our most preferred vote. We only vote for who we want most. But most strong voting systems actually have us cast a voting order where we rank all of our candidate preferences in order. Candidate A, B, C, and D, those are our candidates here, and this grid actually represents a societal preference order. So this is how the entire society would have voted, but the numbers on top actually being the number of voters who voted in that way, and then each column representing the way they voted. So sequential pairs is one of the most probably unique voting systems I've found while I was researching this. Sequential pairs does something really interesting where they actually do a predetermined group of head-to-head comparisons between each candidate. So one might be candidate A versus candidate B, the winner versus candidate C, and the winner of that versus candidate D. And whoever wins the last head-to-head matchup is the winner. So let's go through that one. A versus B. We see that A is above B in the first column, which gives A 22 points. A is above B in the second column, which gives B A another 19 points. And then the last column getting 25 points. We know that our candidate B wins above A in the, look at that. I don't feel nervous. I must be nervous, right? Okay. B is above A in the third and fourth columns, giving B a total of 34 points. So A is preferred above B at a vote of 66 to 34. What would have happened if we actually did a different matchup? What if we had reversed the matchup? We actually would have seen that candidate C would have, or candidate A beats candidate C in a very similar matchup. Candidate A beats with 53 to 47. This moves candidate A on, so we are now looking at candidate A versus candidate D, where candidate D wins 53-47. Candidate D is our winner. If we change that order, if we change that matchup, we change the comparison, let's say we reverse it. So we do D versus C, winner versus B, and winner versus A. We go the other way. That actually gives us A as the winner. What if we had done a different way? A versus D, winner versus C, winner versus B, B wins. One more. We have 4 candidates. We can probably make sure that candidate C wins too, right? Well, as it turns out, we could. This is the issue with sequential pairs, is the ordering was decided before the ballot were turned in, but the ordering decides the winner. It has nothing to do with how society actually prefers the candidates. Now, this doesn't mean a whole lot to us because we don't use sequential pairs, right? Most people haven't seen this voting system before. What we actually vote on is something called plurality. Plurality just looks at who wins the most first place votes, and in that case, B would have won with 34 votes here. This is why sequential pairs exists though. B won with 34 votes. Candidate A was preferred above candidate B by 66% of the voting population. That's enough to overturn a veto, but it's not enough to make candidate A win the election. Something's not right about that. Something feels wrong about that, doesn't it? And something's not right there. So the issue with sequential pairs is actually violates neutrality, and the issue with plurality voting system is it violates independence of irrelevant alternatives. These are both things that we've structured as being almost necessary to have a good, fair voting system, which raises the question, well, what is a fair voting system? Do we have it? What do they look like? In 1972, Kenneth Arrow won a Nobel Prize for proving that there's no such thing as a fair voting system. Actually, what he did was he said the only fair voting systems, and that is voting systems that satisfy both all universality, positive association of individual values, independence of irrelevant alternatives, and citizen sovereignty. Anything that satisfies all of these properties is a dictatorship. So we should probably define these, right? Instead of a lot of words that mean nothing. So universality is that a voting system should place no restrictions on the way voters choose to rank candidates other than transitivity. Transitivity in voting is if candidate A is preferred above candidate B and candidate B is preferred above candidate C, then candidate A should be preferred above candidate C. That's the only way we're going to impose your vote. Other than that, you should be able to vote however you want. Positive association of individual values says that voting systems should be monotone. That is, a winning candidate should not lose by gaining more votes. And likewise, a losing candidate should not win by losing votes. So it should be good for me when I get more votes. Next one would be independence of irrelevant alternatives. This is a societal preference of any two candidates should depend only on the individual voter preferences between those two candidates. I like to think of this one with an analogy. Let's say you're at a diner, and the waiter comes up to you and says, cake or pie? You know, cake sounds really good, I'll take cake. You know what? We have the best waffles though. In that case, I want pie. See, that doesn't make any sense, right? Some third party entered and it changed the way we voted. That doesn't make any sense. Actually, real life example of this same exact thing happening would be the 2000 election. Bush versus Gore. Nader was considered a spoiler candidate, right? And this is one of the reasons that we look at different voting methods when you realize plurality fails because of split voting. Nader was considered a spoiler candidate. But if you really think about it, the way that I pair Bush versus Gore should have nothing to do with Nader. In plurality, it does. Plurality fails independence of irrelevant alternatives. And then the last one there was citizen sovereignty. This says that voting systems should not be imposed. It's not fair if my voting system says candidate A is going to be preferred candidate B because I said so. It has nothing to do with your vote. Those are arrows for axioms, and I'm going to claim that if they are all held, it's a dictatorship. Before we get into that, there's a few limits that are going to help us out. And I know I just went through like a lot of definitions, but I need one more. So I promise this is going to be the last thing I define. Unanimity is if there's a pair of candidates, say A and B, where every voter prefers A over B, then the resulting societal preference should prefer A over B. That makes sense. That seems almost intuitive. But the reason that we're going to use that is because I'm going to cheat. I'm not going to prove Arrow's theorem. He has 4 axioms that are really hard to deal with, but we have a really cool lemma that I've proven. I don't have time to prove it today, but I'm calling it a cheat code because it says that a voting system that satisfies positive association of individual values, independence of irrelevant alternatives, and citizen sovereignty satisfies unanimity. That means I can actually hijack some of the parts of Arrow's axioms that I don't like. I can just substitute in unanimity and make a stronger argument. The second lemma, I'm calling it the all or nothing clause. This is that an election with more than two candidates, any voting system V that satisfies universality, IIA, and unanimity, if every voter ranks some candidate B first or last, then the resulting preference order of V should rank B first or last. This is going to be a very helpful lemma for us in proving Arrow's theorem. So here we have another societal preference order. This time I have every voter listed out, and we're assuming that B is ranked last by everybody. So by unanimity, B is ranked last. Now let's see what happens if one by one every voter starts changing their vote and putting B first. So voter 1 changes their vote. By lemma 2, we now know that B is either ranked first or last, but we don't know which. Voter 2 changed their vote. We still have no idea. Voter 3, the ith voter, we don't know. When the nth voter changes their vote, by unanimity, B is ranked first. So it becomes very clear that there is some sort of a moment. So my first diagram here, we're going to say that B is still ranked last. There's a moment where that switch occurs. Right? So we're going to say that in diagram 1, where voter I has ranked B last, and everyone after voter I ranks B last, the B is still ranked last. I don't know who voter I is, but that's the voter that B is still ranked last. When voter I changes their vote, B is now ranked first. This switch happens somewhere in our voting system. These two diagrams are going to be very important for us, which is why they've actually been labeled diagram 1 and 2. We're going to come back to them later. Right now, we're going to call voter I a pivotal voter, because when I changed their vote, it changed the result for B. And I'm going to prove to you that voter I is actually our dictator. Let's S be a preference schedule in which voter I prefers A over C. And we're not going to make any other assumptions, just that voter I prefers A over C. Okay? Now I'm going to construct another preference schedule. I'm going to call it S prime. And in this one, voter I has B ranked between A and C. So voter I has ranked A, B, C. Every voter before I has B on the top of their individual preference order, and every voter after voter I has B on the bottom. By IIA, none of the changes I just made affected the way that society views A versus C. So this is S prime, I just created it, right? Every voter on the left hand of, look, much better now. On the left hand of I has ranked B first, every voter on the right hand of I has ranked B last, and that's I's preferences. We compare this against our first diagram that we had earlier. It becomes very apparent that if we only look at candidate A versus candidate B, that candidate B was ranked last here, which means that candidate A had to be ranked above it. And this is, in comparison with A, the same exact diagram. So we know that in S prime, A is preferred above B. Now I'm going to look at our second diagram, and I'm going to claim the same exact argument reversed for C. That we know for a fact B is ranked above C because the only thing that changed, nothing changed between B and C relatively. We don't know where B is, but we do know that B is preferred above C. By transitivity, in S prime, A is preferred above C. Right, A is preferred above B, B is preferred above C, A is preferred above C. So in S prime, A is preferred above C, but by IIA, we've already claimed that A versus B is equivalent in S as it was in S prime. That's why we built S prime the way we did. That means that in S, A is preferred above C, but the only assumption that we made about S was that voter I preferred A above C, and everything else was left open. So voter I dictates the societal preference of A versus C. Voter I dictates the rank of B, which we showed earlier, and the ordering of A versus C, which we just showed. So voter I is a dictator who has decided the societal ordering of all three candidates. And it is a good footnote that there's another step to this for something with more than 3 candidates, which I have proven, but only restricting 3 candidates let me fit in the time gap today. And I just want to end on, I want to end with a thought. I mean, this is a Lutheran college, and scripturally, democracy is not Christian. Actually, we know from Revelation that we can expect a time where a sovereign Christ actually runs the world as a dictator. So it's amazing that in a democracy, when we allow people to vote, the only way it's fair is with a dictator. Thank you.
Are there any questions for Devin?
Yeah.
So you said there's no fair voting system. Is there a least unfair voting system?
Yes, there is. I'm going to draw this. I expected this question. So this is actually argued one way from mathematicians and another way from economists. But Donald Sari is a mathematician who argues that the most fair voting method is probably a board account. I'm going to see if I can't draw it up really quickly and make a good example. So if we have A, B, C, B, C, A, and C, B, A, so they each got 3 votes in that way, and their rank is 1, 2, and 3. Board account is a voting system in which we would say that each candidate receives 2 points, or n minus 1 points, ranking minus 1 points for their first place votes, 1 point for their second, and 0 points for their third. And you tally up all the points that every candidate's gotten, and that's how you determine your winner. I'm pretty sure I just made a tie though. Did I? Because we would have A would get 6 points, plus A would get 0 points, plus A would get 0 points. Maybe I didn't make that. So A gets 0 points here. Candidate B would get 3 points, plus 6 points, plus 3 points. Candidate B gets 9 points. And candidate C would
12.
get 12.
Yeah.
Man.
No, that's good.
And candidate C got 0 points, plus 3 points, plus 6 points. So B would be our winner of this election. Donald Sari says that's the most fair voting system we have.
Does he have a proof?
Maybe. I haven't read his book. I haven't. But it's weird because actually every voting system I've looked at satisfies, or not every, but every voting system I decided to focus on satisfies 3 of the 4 axioms. So what do you mean by most fair? Any other questions?